All right, I will begin. You begin with a word of prayer. So, Heavenly Father, we thank you for this time we have just to meet together and talk about abstract algebra. Pray you to guide our thoughts today. Help us to make the most of this time we have, Lord. In your name I pray. Amen. All right, I will start by showing you the solution to the last test. No. Let's see here. Ha ha ha. Let's see here. So this is problem. I don't think you guys had much trouble with this one per se. I won't spend too long on this. Basically, we're asked to show that it forms a group action, so that means that we need to, a couple things. First of all, check that the proposed action actually goes into the sort of object it allegedly goes into, right? So like, if you conjugate a subgroup, is it again, is it again a subgroup, right? So that's the first thing. The thing is that that's the image under the inner automorphism, phi sub a. So if it's the image under an automorphism, it's the image of a homomorphism, then yeah, it's a group. Or you could do the two-step subgroup test if you want. Anyway, the conjugate of a subgroup is again a subgroup. So yeah, this action actually does map into subgroups again. It takes a subgroup to a subgroup, and then you got the identity axiom and the associativity axiom basically to check. So that's obvious. In this one, A star B star H is A inverse, B star H, which is A B H, B inverse A inverse. But then by the sock-shoes property and also just the way cosets multiply on the left and on the right, we have this. And so there you have it. That's axiom 2. There's axiom 1 up here. So it's a group action. And then I figured out that the orbit was just the conjugacy class. Well, it's the set of all conjugate subgroups to H. I don't know if that has a good name except to say that. And the stabilizer here is actually the normalizer of H and G. It's the largest subset of the group with respect to which H appears as a normal subgroup. So, any questions? I know this is a group because we proved the stabilizer is a subgroup, you know? So, next one, denote the set of left cosets. So it's pretty clear. There's nothing, like last time I had to check that the conjugate of a subgroup was again a subgroup because it's not something we worked out before, you know? Here, there's really nothing in that regard to work out because if I take G times the coset XH and I get GXH, that's pretty clearly a left coset of H. So it's definitely the right kind of thing, so the action at least makes sense. And then I just need to check the axiom. So here's the identity axiom, and here's the other one. So AB times this is AB times that, but by associativity of the group multiplication, this is equal to that, and then just undo it. So, any questions about these before I'll try to go through them fast because I think the other ones are more questions about. I'm going to go on. This one here, you know, I'll just say, I mean, I have correct calculations here. And here, let me share with you, because here's what, let's see here. Come on. Here's what Bill said. Come on. Don't undo it. In your discussion, you found, thus, it seems to me, there are representatives for each coset. And he says, this is exactly noticing the redundancy of the representatives of an orbit is accounted for by the stabilizer. That's the orbit stabilizer theorem. So what I'm hearing is what I saw as Lagrange's theorem is really the orbit stabilizer theorem. And that's kind of okay. I mean, fine. the orbit stabilizer theorem is a generalization of Lagrange's theorem. All right, so it's kind of a question of philosophy. I was trying to see like an explicit, distinct use of the orbit stabilizer theorem besides Lagrange's theorem for this HK problem, and that was a mistake on my part. Like basically, you can go back to the earlier solution and just try to say, okay, how does this earlier solution, how can I understand this in terms of some sort of group action? Like that would be philosophically what to do with that problem. In short, let me just kind of encapsulate it here for you. Where was my stupid thing? Basically, all I'm saying is you can look at problem 60 if this is confusing to you. Okay. We talked about this in class. Let me go on. We talked about that in class. The one thing currently missing from the homework solution is Cauchy's theorem in the abelian case. I didn't have a chance to find that yet or prove it. I showed you these ones yesterday. Let me go on. Here's one I'll go through. So suppose you have A and B are a subgroup of G, and A is a subgroup of the normalizer of B and G. Then we're supposed to prove that AB is a group, a subgroup of G. All right? So what does this mean? The normalizer of G and B is G and G, such that GBG inverse is equal to B again. So in other words, they're the set of group elements which conjugate B to B. And so if you look at what that does then, if A is a subgroup of this, that means, if you think about it, right, that means that A belonged to this club, right? So A inverse is equal to B for all A and A, right? If A is a subgroup of the normalizer, that means that everything in A normalizes B, right? So in particular, we have that equation, which means that we have the left and right cosets of left and right A cosets of B. How can I say this? Anyway, it's most precisely accounted for right here. AB is equal to BA, where A is any element of A. All right, so then I'm trying to show that this is a group. You guys can see it's not empty because if A and B are subgroups, E is in both of them. So E times E is E, which is an element. In other words, this is not empty because the identity's in there, so we can apply the one-step subgroup test. Let's do that. So pick X and Y in the product AB, all right? That means that there's an A1 and A2, a B1 and a B2, such that X is the product of A1 and B1, Y is the product of A2 and B2. That's what it means for X and Y to be in here. So then when I look at X times Y inverse, right? Remember, Y is not some abstract point in Nowheresville. I mean, it's an abstract point, but it's in a group, right? So these elements are products in a group. The larger, the supergroup, the G, which everything is happening, the universe in which everything is happening here, G is a group. So I have sock shoes. I have all the usual rights and privileges, calculational, this and that for group elements. So I can do sock shoes here. All right. And but then look what you got. You got A, B1, B2 inverse, A2 inverse. I'm trying to reformat this so that it looks like something A, something times B, right? So this A is where it doesn't belong. But the thing is, I know that I can move A's and B's around using that normality condition I just stated. So I know that BA2 inverse is equal to A2 inverse B, right? Because A2 inverse is an element of A. So that allows me to trade B1, B2 inverse, A2 inverse for A2 inverse times B3, where B3 is just some element of B. This is even stronger. Some problem I worked before, I remember I wasn't allowed to have the same A here, but this is even stronger than that. I even have the same A element both sides in this sense here. But whatever. Contrasts aside, there you go. Something in A, something in B. So XY inverse is in AB. One-step subgroup test. We're done. Any questions about this one? Anybody get this one? Jess thinks he got it. That's good. I mean, I think the main struggle here was to internalize what on earth it meant for A to be a subgroup of the normalizer of B, right? That's kind of scary, hard to digest right away, at least for me. Yep.
So for like questions like finding orbits in the test, like I know in one case, like, are we expected to like, if we turn it into something, let's say we find the set of the orbit, we define it in terms of like set notation?
Well, it depends on the instructions. You know, if I say describe the orbits geometrically and they're circles, I want you to say they're a circle.
Okay.
You know, if I just say find the orbits, then maybe a set, you know, a set builder notation with here's the object, here's the condition, maybe that suffices.
Do you expect us to like, they expect us to be able to like transition between like set thing and like if we find it's like a specific like how to do like the normal group?
No, Mr. Gregory, I expect you to fail. I'm sorry, no. Sorry. Sorry, I saw Spectre appeared in Amazon Prime recently. But, you know, it depends on the problem, like how do you want to find the orbit? I mean, I don't know. I mean, it depends on the group action. How do you want to express it? It depends on the group action. You know?
I didn't know if like when you like say like find the orbit, it's like we always find it in terms of like some other like term, like say like normalizer or like the center or like the...
Yeah, well, there's some, right, for the group action of conjugation on the group, the orbit and the stabilizers are other things.
Yeah.
Right? Or the fixed subgroup was a center, I think, if I remember right.
Yeah.
So yeah, I mean, if it happens to be something else that has a name, then you can name it, right? But I try not to do stuff like, you know, here's a group, name it, and then my students think about it for hours and hours, and then, you know, you get it back, and I go, so what did you name it? And you're like, no, I said name the group. So like, you should name it, you know, like call it George or something. I actually had a topology homework like that once. He said, name this topology. And then when we got it back, he's like, no, I meant to name it. I was like, you monster. Anyway, that's much worse than here. You actually can name the thing. I mean, if it's a low-dimensional group, at least if it's up to order 7, we can, up to isomorphism, name it, right? Or if it's a cyclic group, you can classify it as one of our Cartesian products of, you know, if it's a finite abelian group, up to isomorphism, we can figure out what it is, right? Given, you know, if it's a group of units, we can use our tricks and techniques to break it down to z cross z cross z cross whatever modulus, appropriate mod this and that. This one, excuse me, prove that K mod H is a normal subgroup of G mod H. I would point out, okay, so first of all, H is a normal subgroup of G, which means that I have that GH G inverse is equal to H for all G, but that also means that GH G inverse is equal to H for all G and K, because K after all is a subset of G. So first of all, this makes sense, right? In other words, H is normal with respect to K, so I can form this quotient. Point number 1. Point number 2, so it's a factor group, all right? And so I can then study, so I know it's a group at that point. So now I just need to figure out if it's normal with respect to GH. So I need to study conjugation by a GH element, right? Which in this case is something like GH, and something in K mod H has the form XH where X is in K. So this is equal to that. Nothing much changed there, did it? Just this, that the inverse of the coset is the coset of the inverse, right? This you know from your study of cosets and factor groups. If you don't believe it, you can prove it. Check it out. If I take G inverse H times GH, I get GG inverse H, which is also known as H. So there you go. G inverse H is the inverse of GH. This is not hard to prove. Anyway, so that's that. Then multiply cosets as we do, right? Multiply representatives. Normality guarantees that that makes sense. Multiply again, so we get GX G inverse. But hey, GX G inverse is an element of K again because K G inverse is equal to K again, right? Because K is normal. And so this is an element of K mod H. which is to say that the conjugation of K mod H by a G mod H element is again a subset of K mod H, which is to prove by theorem 9.1 in Galilean that the K mod H is a normal subgroup of G mod H. And then this is, once you've got that out of your system, the rest of it's pretty easy, honestly. So first of all, is it well defined? Whenever we have a mapping on cosets, we should check that the formula is independent of representatives. So how do you do that? Suppose you got two different representatives, G1 and G2. What does that mean? That means that G1, G2 inverse is an element of H, right? H is a subset of K, since it's a subgroup of K. So that means that G1, G2 inverse is an element of K, which, by the way, means that the left and right, the left cosets of G1 and G2 with respect to K are also equal, which is tantamount to saying that this function is single valued. See, because phi of G1 is G1K, which is G2K, which is phi of G2. So it's independent of my choice of, and I should have G1H here. Typo, H. Right? Oops, I think I left a mark. Anyway, so don't tell anybody. Let's see here. So that is that, which by properties of, coset multiplication is that, which is that, homomorphism. And the kernel, I'm looking for xh such that the image is k again, because that's the identity, right? And so that's xk equals to k. Well, that just means that x is an element of k. So I'm looking for cosets of the form xh in G mod h such that x is an element of k. Well, that's just K mod H. That's the cosets of H with representatives taken from K, which is K mod H. And so that's the kernel. And then finally, first isomorphism theorem finishes it. So we have a mapping from there to there. The kernel is this, which is a normal subgroup of G mod H by our theorems. And by theory rather. And it's easy to see it's a surjection, right? If you pick anything in here, then xh maps to that. So it's surjective. This was not hard, right? Okay. And so, I mean, I suppose if you didn't say this, but you just claimed it in a problem, I would probably not take off a lot of points. It kind of depends on how easy the problem is. If it was a very easy problem, I might take off half the points, right? It kind of depends on the nature of the problem, Yeah.
Is there any case for like finding a key function, like not being very evident, such as like that, like finding a homomorphism?
You don't think this is a natural homomorphism from here to here?
Well, no, I think like I'm asking like, is there any like a case where there's ever going to be it's going to be difficult to find a homomorphism?
Are there places where it's difficult to find the homomorphism from one group to another?
It seems like almost.
Yeah, I would say the ones that are small groups where it just basically amounts to pattern matching. For me, those are kind of laborious. Like finding the isomorphism from S3 to something else that's isomorphic to S3. You might not have a formula for it. You might just kind of have to sort through generators and relations until you figure out, oh, there's my transposition thing, there's my 3-cycle thing, and how to, I don't know, those, to me, those are harder. When I have a formula with a determinant or cosets and stuff, it's easy. I don't know, I mean, you got to map things to apples and oranges to oranges, right? If you got an element of order 2, you want to map it to an element of order 2 and kind of extend from there, things like that. If you have a generator, if you have cyclic group and cyclic group, you map generator to generator, right? There are things like this to think about.
It just seemed like every time I found a homomorphism, it was like the trivial.
They always seem trivial when somebody else writes down the formula, yes. I will admit that is true. Or when I copy them out of a book, in this case. Anyway, I can't take credit for this. If this, of course, is from, what I did was I took Dummett and Foote's proof for the third isomorphism theorem, and I deconstructed it for this homework problem, Anyway, this, of course, then G mod H mod the kernel is isomorphic to the image, but the image is exactly G mod K because it's onto, and that's exactly K mod H. So there you go. That's the third isomorphism theorem, right? Yes, Bradley.
Back when
Yeah.
And then you said that implied that both were elements of H. How do we get to that?
I began by supposing that G1H was equal to G2H. So that means that G2 inverse times G1 has to be an element of H.
Right, but then you get that each individual. Oh wait, no, you didn't do that.
No. I just used it again to say, oh, but that's a subset of K, so that means that the G1 and G2 cosets of K are equal as well.
But you're not saying the individual elements are also.
No, I'm not saying that. I'm saying they have matching cosets. Matching H cosets gives you matching K cosets is the thing. Yeah. This one is actually kind of fun. So here's the subgroup lattice. Make it a little bit smaller. Here's the subgroup lattice of Z12, right? So you got generated by 1. You can look subgroup generated by 2 or 3 or 6 or 4 or 12. So like 2 has 0, 2, 4, 6, 8, 10, right? The 3 subgroup has 0, 3, 6, 9, so it's got 4 things in it, right? And the 6, what does it have? It's got 0, 6. It's a subgroup of order 2, right? The 4 has 0, 4, 8, so it's a subgroup of order 3. And this is how they're situated one inside the other. This is the subgroup lattice. So if you look at the factor groups by the lattice theorem, or I think Dr. Sprano calls it the correspondence theorem, the fourth isomorphism theorem. If I look at the factor group of Z12 mod the subgroup generated by 2, right, that would be this here. And so the rule was, it said basically everything down here goes away. So it just leaves you with just that part of the subgroup lattice. So it's just that. And that is the lattice for Z2. Z2 just has the whole group and the identity and no subgroups. That's the lattice for Z2, by the way. So this is, of course, not Z2 technically speaking. This is Z12 mod 2Z12. So like, so Z12 mod 2, we could also write as Z12 mod 2Z12. This is notation. You had another homework where you proved that that was isomorphic to Z2, yeah? Remember that? So that's at play here. Technically speaking, this is not equal to Z2, right? But it's isomorphic. This is a factor group. This is actually, this is really two, stupid curses. It is 0, 2, 4, 6, why am I doing this? 8, why did I do this one? 10, plus, and the other thing in here is 1, 3, 5, 7, 9, 11. So this is the 2, this is the 1 plus 2. These are the 2 cosets that are in here. But that's isomorphic to Z2. All right. Okay. Where was I? This one's also very boring. So like if you just look at the factor group by 3, everything below it gets squashed out of the diagram, and you're just left with this diagram, which is Z3. So these two have the same diagram, and yet they're not isomorphic, right? Non-isomorphic groups can have the same diagram. But isomorphic groups have the same diagram. So it's like, yeah, exactly, necessary but not sufficient. This one's interesting. If we cut out 6, if we look at the factor by 6, well then we've got this diamond left over, and then these guys are gone. And then finally, if we look at the lattice, the factor by the 4 subgroup, that leaves these guys. Everything over the 4 survives, but everything not over the 4 is gone. Gone. And that just leaves us with this little lattice. So you got basically Z mod 4. Z mod 4 has, anyway, the cyclic group with 4 elements has a subgroup of order 2, and then, of course, the identity at the bottom. And that's that. Any questions about this? I personally enjoyed this homework. This particular homework problem I enjoyed. It was fun. Are you happy I didn't stick with like the 25 I had there to start with, or 100? Did I get? Oh, I should show you guys something. Again, by the way, if you guys want to see my deliberations on the HK problem, they're all here to read. So you can see, apparently it's just a matter of philosophy. It doesn't click in my head yet. It's not, what we did not wrong, it's just not, I lack motivation or something there, I don't know. Okay, so where is it going to? Oh, yes. No, I don't want to do that. Nope, do not, nope, remove, go away. I've got too many bookmarks. Sea of Red, you guys seen that? Okay. Check this out. So you want to look at the subgroup diagram of like, there's 12. There's the Cayley table for Z12. Yay! Subgroup diagram. I said show diagram. Huzzah! There it is. That, I guess, is not impressive. But how about, here's a subgroup diagram of like 3, 8. Oh, there's the Cayley table for Z3 cross Z3, 8. Here's the subgroup diagram. Well, it's not too bad yet, is it? Anyway, this is kind of fun to play with. So, I don't think I sent you guys a link to that, and I probably won't. But if you use the Google, you can find it. Where was I? Would you like me to send you a link? I can send you a link if you want me to. You can waste an inordinate amount of time playing with subgroup diagrams. It's fun. Oh, this is the last one? Yay. Yeah, so there's really not much to this problem. You're supposed to show it's a homomorphism. So like if I take the sum of two polynomials, f of x plus g of x, then by definition, that would be, I mean, I guess you could, anyway, it's f of 3 plus g of 3. But what's f of 3 plus g of 3 is psi of f of x plus psi of g of x. So yeah, it's a homomorphism. I could make it more complicated, but why do so? Now, psi is, what's the kernel? Well, that's f of x such that f of 3 is 0. All right, so by the factor theorem from high school algebra, remember? We know that if you have a polynomial with 3 being 0, that means you can factor out x minus 3. So I guess one way you could look at this is the kernel of phi is polynomial multiples of x minus 3. But I looked in the back of Galilean because I wanted to see what he meant. Apparently he's looking for geometric. So fine, here's the geometry of it. It's all the polynomials that go through 0, 3, right? The graphs of the polynomials, they're all going through there. So it's an infinite set, right? This kernel. But there it is. Now, if you were actually writing out like a0 plus a1x plus a2x squared and so forth for this problem, you could make the problem look way, way more complicated than it is, right? So when we're talking about function evaluation, it pays off to stay at the level of function notation sometimes. Anyway, I think that's all I got. Do you guys have questions about anything? Yep.
I don't know if you went through this already. I did come in a little bit late. Could you explain real quick for me exactly what you mean by an orbit geometrically looks like a circle?
Oh, that problem. You're right. I was supposed to go over that one today. I have not done that yet. 2018? Yeah. So, I mean, is orbit always a circle? No. Could be lots of things. right? But for this rotation, these are orthogonal matrices. I think we had a problem earlier where I connected this to these being precisely the matrices of transformations which fix the origin and leave the distance between points unchanged, if I remember right. Anyway, these are the orthogonal matrices. And so if you calculate the determinant of this, you get plus or minus 1. So there's some of them that have determinant 1, some of them have determinant minus 1. The ones with determinant 1 are actually rotations. The ones with determinant minus 1 turn out to be reflections. And that's it. It's rotations, reflections, products thereof. That's what orthogonal transformations are. Anyway, we're supposed to calculate the orbit and the stabilizer for each point in the plane. The orbit of the origin is easy. See, because, well, if you look at, r times 0, any matrix times 0 is just 0 again, right? So orthogonal transformations don't move 0. They just keep 0 at 0. Not surprising, they're linear transformations. So of course they don't move 0. But on the other hand, excuse me. On the other hand, if v is not equal to 0, then if you look at r times v, rv, well, that has magnitude rv squared, which is the dot product of it with itself, which by the way is rv transpose times rv. And then what's that? So that's v transpose rv, which is v transpose I, which is v transpose v, which is v squared. So the distance from the origin of rv is the same as the distance from the origin of v. That says that the image rv lies on a circle that has radius length of v. So the distance from the origin is the same of the moved point, of the initial point. That says that the orbit lies on a circle. Or if v is equal to 0, it says it stays put.
And that's just because this orbit is defined by
Multiplication by an orthogonal transformation, yeah. If it was just any old matrix, the orbit would be something else. Like if you asked me what the orbit of a point by the 1, 2, 3, 4 matrix in the plane was, I wouldn't know. It's something. It's different for different points. But it doesn't give you circles. It gives you something else. Let's see here. Where was I? Oh, yes. Now, but then I wanted to show that the orbit is the whole circle. So that obligates me to show you that I can take that initial non-zero point and move it to any other point on the circle. And that's where the heavy lifting comes in here in terms of the solution, a little bit of it anyway. So basically I have to draw a picture and let angles do their magic. So let's suppose that the given point V is at standard angle theta. That means I can write the point in terms of this, in terms of polar coordinates. And then I want to, this is the point I want to move to. The point I'm given, V, is at theta naught, at angle theta naught. And so I argue that if you rotate by theta minus theta naught, it ought to move this over to there. And that being arbitrary shows me I cover the whole circle with the orbit. And so I'm geometrically motivated to write this rotation down. And you can see it works because adding angles formula. There it is. So I can map to P. And so that gives you that the orbit is a circle centered about the origin through V. So then, let's see here. Excuse me. SO2 with the determinant 1 matrices, they are they're the kernel of the determinant map. So that means they're a normal subgroup. So that means that the cosets of SO2 partition O2. So there's either the rotations, there's the reflections, let's see here how to say this. So basically O2, it's either the SO2, the determinant 1 stuff, or these. There's these two cases this, and then it's left coset by 1, 0, minus 1. And so a rotation in SO2 can be shown to have the form cosine, sine, minus sine, cosine. Fine, that's a gap in my solution, admittedly. I haven't actually proved that. But on the other hand, the coset of this, if I take 1, 0, 0, minus 1 times the sine times the rotation, that gives me this. So altogether, an arbitrary 2 by 2 orthogonal transformation has the form cosine, where was I? Cosine, sine, minus epsilon, sine, epsilon, cosine, where epsilon is plus or minus 1. That's everything. That completely describes all of the matrices in O2R. That's just basically a parameterization of an arbitrary element there. And so with that, I can calculate the stabilizers. So I'm looking for fixed points. I'm saying this rotation times xy gives me xy again. That makes it a stabilizer, right? And so that equation gives me this equation. And the unknowns here are cosine theta and sine theta. And basically, we're going to break the calculation up into two parts. Epsilon equals 1, epsilon equals minus 1. So the epsilon equals 1. So that, anyway, but for either, I have this star equation, which is just linear in the given point xy, and the epsilon, which can be plus or minus 1, the cosine sine, which I don't know, but I want to figure out. And so that's a linear system. You can solve it. And do that over here. Epsilon equals to 1 gives me cosine sine is equal to 1, 0, which is to say that cosine is 1 and sine is 0. In other words, it's the identity rotation. Right, so that's the one thing in the stabilizer is the identity. We knew that was there. That's not surprising. The stabilizer subgroups is subgroup, so it has the identity matrix in it. And then the epsilon equals minus 1 gives me the other thing, which wasn't immediately obvious to me, which was that there's a rotation, there's a reflection. And so solving this via multiplication by the inverse matrix basically gives me cosine is this and sine is that. And so r sub v is this. And you can check that if you multiply r sub v times xy, this mess works out to x squared plus y squared times x, and this works out to x squared plus y squared times y. So those cancel and give you xy back again. You can see it's a fixed point. And that's it. So the stabilizer is Z2. It's got the identity rotation and the rotation. And geometrically, this is like so obvious. If you pick a point, right, and you ask about rotations and reflections that fix the point, right? So the one thing that fixes the point, of course, is the identity rotation, obvious. And the other thing you can see if you think about it for a little bit is that if I have a reflection, about this line, it doesn't change the points on the line, right?
Yeah.
So there's just one of those in O2. And so that's the stabilizer. It's the identity rotation and that. Simple to see. Right? I mean, I think in the future I will entitle this problem Geometry's Revenge. Because it's like, yeah, you guys can do all that algebra, but it hurts a little, yeah. So, yeah. This took me a while. Oh man, but wasn't this problem well welcome? Wasn't this nice? This was a beautiful problem after that problem. This was so refreshing and uplifting, this problem after the other one. I mean, it was, is it just like, it's so easy. This one. This actually is useful too later as we study extension fields. But anyway, I like problem 71 too. No Kendusville. And here's, well anyway, are there any questions? I'll stop scrolling. You have a question, Bradley?
No.
No? All right.
Well, I do remember the newer version of that problem that you scratched in the first homework that you reassigned to Wednesday, the last problem. I think it was 72.
This one?
That one, yeah.
Mm-hmm.
That was fine, but I couldn't get it to work if k didn't divide n, but k did divide n. Like in that scenario. Which would be one of the cases if k divided mn.
Well, I know that the problem as it's stated now is good. I mean, here's the proof. If k divides mn, we get this sensible mapping. And more than that, this calculation shows that that has to be the form of it. I mean, essentially the point is this x, x sub n is equal to x times 1, right? So whatever happens to 1 is connected to what happens to x in this way. And that's very important.
I just
Now,
didn't understand why you would say k divides mn rather than just k divides n.
well, I need k divides mn here.
You do.
Yeah. I mean, look, so if phi of, look at this argument here. So suppose that 1 maps to m. It's got to map somewhere, right? So if it maps to m, for some m, on the other hand, we also have that 0, right, maps to 0 because it's a homomorphism. But 0 is also n sub n, which, by the way, is n times 1. And by the way, I can pull out the n because phi of nx is n times phi of x. That's what phi of g to the n equals n phi of g to the n looks like in the additive notation. Like that's the homomorphism property n-fold times. And so that means that, what does that mean? In other words, n times m, right? Which is, by the way, nm, k coset of mn equal to 0. But that means that k divides mn, so it's just that. Now, I did replace the earlier problem with something that makes sense if you guys go back and look at it. It wasn't one I assigned, I just threw something in there to give you something interesting to chew on. Which problem was that before?
It was 3 days before.
3, it says 15?
It was the second one.
Yeah, here it is. So I modified the problem to make it more interesting, like logical. So instead of just what was there before, I said, suppose you have a surjective homomorphism, right? If that's the case, then the first isomorphism theorem says that Zn mod the kernel of phi is isomorphic to Zk, but the size of Zn is n, the size of Zk is k, so, and the size of the cardinality of the quotient is the quotient of the cardinalities. Again, I feel silly to say cardinality here. They're just sizes, like number of elements in a finite set. And if they were infinite, I don't know if the quotient still makes sense, and I don't think it does. Anyway, so n divided by this number is equal to k, which is to say that n is some multiple of the kernel phi, right? In other words, k divides n. So if I had added the criteria surjective homomorphism, the problem would have made sense. Although, still, the bit about the m and the k divides mn still would need fixing. But the part I just looked at in the other problem was correct. It was always correct. It was the show that k divides n, which was nonsense. It doesn't have to be the case, right? So.
Which is what I was the k divides n.
Right. Unless it's surjective, in which case it is the case. Of course, my counterexample was not surjective. Z6 to Z4, 2x. It didn't cover all of Z4. Yeah. Well, anyway, I think that's all I got for you guys, unless you got a question. No? All right. What makes this day so special? Why so many people here? Can you turn it off for me? Thanks. Excellent.